Welcome to today's session on cryptographic use cases and techniques, based on CAS-005 Topic 3.8.1. Let's start by understanding different cryptographic use cases in simple terms, with examples you can relate to. First, data at rest. This refers to data that is stored on a device or server. We protect it using encryption methods like AES. For example, encrypting files on a hard drive or securing backup databases ensures that even if someone steals a physical device, they can't read the data without the encryption key. Next, data in transit. This is data moving from one place to another, such as over the internet. Encrypted tunnels like VPNs or HTTPS connections help secure data as it travels. Think about logging into your bank's website. SSL certificates help encrypt your information from your browser to the bank server. Now, data in use. This means data being actively processed by a system. Protecting this is harder, but some technologies like homomorphic encryption and trusted execution environments can help process encrypted data without exposing it. For instance, cloud services might process your data without ever fully decrypting it. Moving on to secure mail. Secure email systems use encryption standards like SMIME and PGP to make sure only the intended recipient can read the message. It also ensures the sender is verified and the message hasn't been altered. This is critical for legal, business, or medical communication. Immutable databases and blockchain. These are systems where data, once written, cannot be changed. Blockchain is a great example. It's used in cryptocurrencies and can also store contracts or records securely. This immutability prevents fraud and supports data integrity. Now, let's talk about non-repudiation. This ensures that someone can't deny having sent a message or perform an action. Digital signatures are a perfect example. When you sign a PDF with your private key, the recipient can prove it was you, and you can't deny it later. Privacy applications. Cryptography enables tools that protect user privacy, like encrypted messaging apps such as Signal or WhatsApp. They use end-to-end encryption, so no one, not even the company, can read the messages. Legal and regulatory considerations. Laws like GDPR or HIPAA require sensitive data to be encrypted both at rest and in transit. Failing to use proper encryption can lead to fines or lawsuits. Organizations must choose crypto solutions that comply with these regulations. Resource considerations. Not all encryption is equal in terms of performance. For example, full disencryption may slow down older devices. So, there's always a trade-off between security and speed, especially on mobile or IoT devices with limited computing power. Data sanitation and anonymization. Sanitization means securely deleting sensitive data so it cannot be recovered. Anonymization, on the other hand, removes personal identifiers from data, making it safe for research or public use. For example, hospitals may anonymize patient records for medical studies. Now, let's cover the additional cryptographic topics. First, certificate-based authentication. This uses digital certificates to verify identity. Instead of passwords, users or devices present a certificate signed by a trusted authority. It's like a digital passport. Widely used in VPNs and enterprise networks. Passwordless authentication. This is becoming more common. It uses biometrics, mobile push notifications, or hardware tokens instead of passwords. For example, Microsoft Hello or Google's passkeys let you sign in without typing a password, reducing the risk of phishing. Software provenance. This refers to verifying where software came from and ensuring it hasn't been tampered with. Developers can digitally sign their code, and users can verify the signature before running the software. Software or code integrity. This ensures the software hasn't been modified or corrupted. It's done through hashing and digital signatures. When you download an app, its hash value is checked against a known good one to ensure it's safe. And finally, centralized versus decentralized key management. Centralized key management stores and manages keys in central server or HSM, making it easier to control access. But it can become a single point of failure. Decentralized systems distribute key control, like in blockchain or peer-to-peer encryption, providing more resilience but adding complexity in managing those keys securely.